Oh, sorry, I didn't share my I didn't share the whiteboard. So, analysis of variations. Дисперсионный анализ по-русски. And to begin with, let us discuss a real-life example that shows the effect that I want to discuss. Assume that I'm a teacher and I have a class who write a test. And I suspect that some of my students cheat and copy from, for example, from their neighbor. And assume that I know that the students don't know correct answers to some questions. For example, I give them some kind of test or some kind of other work that they should write. And I understand that if I see similar mistakes in two works, it can be probably considered as an argument that they are cheated and that some of them just copied work of another student. And actually, if I'm interested in this problem, I do a kind of statistical analysis. In fact, people don't actually do a rigorous statistical analysis, but the logic is the same as we discussed previously. If I have similar works, assume that I have, for example, two works. This is work 1, and this is work 2. Assume that this is work of Alice, and this is work of Bob. And if I see that there are too many identical incorrect answers, for example, something like this. So I see that these answers coincide, and they are incorrect, and these answers are different. But if I see that I have a lot of coinciding incorrect answers, I can suspect that these students are cheated and they probably copied from each other or communicated during this exam or something like this. And then I have to decide, do I have enough evidence to accuse them in cheating? And I do it like I do my statistical testing. Namely, I understand that it is possible that there is some coincidental that it is possible that some equal answers can it is possible that people produce similar works just by coincidence. For example, if I have like yes or no test, it is possible that some answers, even incorrect, will coincide even if they do not cheat. But if I see a lot of these coinciding answers, then I can say that, okay, it doesn't seem to be like a coincidence because the probability of such a coincidence is too small. And so I will say that it is a good evidence to accuse students in cheating. So my logic is the following. For example, I count how many answers, incorrect answers coincide. Of course, correct answers should be coinciding because they are correct. So we can think about multiple choice test. For example, I have 4 options for each question, and then there are 3 possible ways to be wrong. And if I see that in 2 works, these incorrect answers coincide, and the number of these coincidences is rather large, then I can accuse the students in cheating if it is large enough. Do you agree with this general logic? Do you agree that probably a teacher can use this logic when they try to understand, is it true that 2 students copied their work? Does it look reasonable for you? This is not.
I would say generally yes, but of course we can
Yeah, this is actually not about statistics. This is just about common sense. This is how people actually do. Uh, this is actually how people make such kind of decisions, right? If any of you even worked as a teacher, or and you know that if you see 2 very similar works, you will say that probably the students are cheated, and then you grab the student and ask them why you gave me so yeah, similar works, and they say we don't know. This is just a coincidence. We worked independently, and then you have to put some threshold that if you see that there is too much coincidence, then well, you say no, I don't believe you. You are cheated. And now the question is how to understand what is large enough. And this is where probability came into play. And we say something like this: large enough is so large that probability to get so many coinciding incorrect answers without communication is small. So basically, we do statistical hypothesis testing here. Uh, what is null hypothesis here in this setting? Let us restate this problem in terms of our null hypothesis, alternatives, and so on.
that the absurd. Mm, yeah, probably Sonia. It's that they did not cheat, and I would say that the absurd number of coinciding answers is not uh, could be the result of independent work.
Mm-hmm. So actually, the result that we obtain in any case can be the result of it is possible to obtain any level of coincidence just by chance, any level of equal answers, but the probability decrease as number of these coincidences increase. So and to state this in statistical terms, indeed we have to state null hypothesis. And actually, Sonia is correct. Null hypothesis here is that they do not cheat. And actually, Natalia is also say something close. As far as I understand, you said that under the null hypothesis, we explain, if we believe in null hypothesis, we say that we explain the coincidence in the work that we have just by randomness. So this is actually what we say in null hypothesis, that they do not cheat, and we have an alternative that they are cheating. They are cheating. And then if you look here, you see that we do actually just an ordinary statistical testing. We ask ourselves, what is the probability to obtain the data that we actually obtained? In this case, our data is count how many incorrect answers coincide between two works. And we ask ourselves, what is the probability of this result, or even more extreme result, under a condition that null hypothesis holds. So under the condition that they do not cheat, or they do not communicate with each other. And actually, this is the logic that you use, I think, every time when you have to make some decision from some information that has some randomness. And this is basically the idea of statistical testing. I just recall it because now I need to discuss rather specific version of the statistical testing. Let us okay. Let us assume that we will do the following. As usually, to denote what does it mean that some probability is small, we fix some significance level. Like, for example, I want to be sure that if they do not cheat, then I will accuse them in cheating with probability, for example, less than 1%. So in any case, it is possible that I will be mistaken, and it is possible that I will accuse them. I will do wrong accusation. It is possible, but I just want to reduce the probability of this event in such a way that this probability is smaller than some level. So let us use some really small significance level. It means that we accuse them in cheating if probability to obtain the same number
But why the significance level is so small?
Well, I just really afraid of making false accusations, and so I put here
Mm.
1% instead of the usual 5%. So I understand. I understand that I will. It is possible for me to make false accusation, but I really, really, really do not want to make type 1 error here. I really do not want to accuse students falsely. So we accuse them in cheating. Its probability to obtain the same number of coincidences between works, provided that null hypothesis holds, is smaller than alpha. And if I use this procedure, it means that probability to falsely accuse students, provided they did not cheat, is less than or equal to alpha. So in this case, 1%. Um, so this is my procedure. I do not want to discuss now how to find exact uh, the exact threshold number, how many coincidences I have to consider to actually get this probability. Assume that I have some way to find it. So now this is formalization of our testing, and now let us consider a more real example. Actually, in this discussion, we consider it only a pair of students. But of course, if I teach a class, I have not just two students, I have a lot of students. And let me assume that I have something like this. I have several tables, and I have two students at each table. For example, I have 10 tables. And I understand that during the test, these pairs of students can cheat, can communicate with each other. And then I apply the same procedure for all tables. So I compare pairs of works, and for example, I have work here and work here. I don't know. It seems that it is completely impossible to understand what I tried to draw here. It is a table like from the top. These are two students. This is a table, and these are their works. And we compare pairs of works at each table, and we apply this procedure for each table. We apply it to each table. And now my question is, what is the probability? So apply the described procedure to every pair of work, to every table. And I have a question. What is the probability to make false accusation provided that nobody cheated? So if I compare two works, if I consider one table, I know that my procedure by construction gives me probability of false accusation to be not larger than 1%. Let us assume that it is exactly equal to 1% for simplicity. What if I have 10 tables? Okay, it may be not very.
It should increase. It
should increase. Yeah, this is actually the main point. You're absolutely correct. It will increase. It will be larger than alpha. Yeah.
10%.
Well, 10%. We have to find it. It doesn't work like this, because if I had, due to your logic, if I had not if I had not 10 tables but 1,000 tables, your probability will be equal to 10. It doesn't work like that. We will find this probability just in a few minutes. But actually, even before we find it exactly, we see that this probability will be larger than 5%, well, larger than 1%, larger than this alpha. So I have probability of false accusation. Here it is 1%, here it is 1%, here it is 1%, and so on. Here it is 1%. But the probability that I will accuse falsely somebody of them is larger than 1%. Do everybody agree with this idea?
But I do not understand. Do we want to know whether they all cheated from each other? I mean, all 10 tables have the same answers, or
no. We compare just works between inside one table. So I compare this work with this work with this work, and so on. And actually this is what actually happens. If I have a class, then I will collect their work, and I will assume that I know who sits near who, and then it is reasonable to compare the works of two students who sit at the same table.
But I do not understand why we need to find out the probability for 10 tables simultaneously if we can just find it for each table. I do not understand why we do it all together for 10 tables. Why do we need this probability?
Look, I'm interested in, okay, I don't want to accuse students. I don't want to falsely accuse students in cheating. And my idea is that as I increase number of tables, I increase probability of this false accusation. Even if I control probability of false accusation for a particular table, if I ask myself, what is the probability to falsely accuse somebody, I have to answer the question that is asked here. So assume that I have not 10 tables, but for example, 1,000 tables. right? In this case, I will increase probability that I will accuse somebody falsely even more. And what I don't want is I don't want to accuse somebody falsely. You see the point? Actually, what is important for me is not that is not the probability to falsely accuse some particular pair of students. I don't want to falsely accuse any of the students that I have. So I have to find this probability.
So we.
Yes, Ksenia?
It seems that I still do not understand why we need this.
Okay, assume that probability to falsely accuse some of the student is, for example, 80%. It is not correct for these numbers, but I assume that a number of tables is so large that my probability to falsely accuse some of my students is 70%. So it means that almost on every test, I will falsely accuse somebody in cheating. How do you think? Is it good? Is it good decision process? Is it good for me as a teacher, and is it good for my students? That some of them are accused in cheating, even without any cheating from their side, just because they are unlucky, just because due to simple coincidence, they provided similar works for me.
So I just can't, maybe it's because I can't imagine it in reality, because usually you want to count this probability when you see that the tests are alike, but here it's not the case, yes? So I still can't
не
get
совсем
it.
понимаешь, может быть, проще, если вы по-русски спросите, я не совсем понимаю.
Ну, я, в принципе, не понимаю просто, зачем нам вероятность обвинить их всех.
Ну как, потому что это та величина, которую я хочу сделать маленькой. Как бы если так оказалось, что я там на каждом втором тесте кого-нибудь случайно обвиняю в том, что они списывают, хотя в действительности они не списывают, ну как бы это, наверное, не то, что я хочу.
Ну, а зачем всех рассматривать? Я просто не понимаю.
Ну, представьте себе, что вы студент вот такого преподавателя. Значит, и вы знаете, что там, с вероятностью 50%, допустим, вы точно знаете, что никто в вашем классе не списывает, но вы знаете, что с вероятностью 50% кто-нибудь будет случайно обвинен в списывании, потому что вот работы случайно совпадут. Мне кажется, что это именно та вероятность, которую мы хотим контролировать в этом случае. Ну, реально, это вот именно то, что я хочу сделать маленьким. Я хочу сделать маленькой любую ошибку. Ошибку в отношении любого студента.
То есть
я
мы
правильно понимаю, что вот если у нас много очень тестов, то просто становится больше вероятность, что они совпадут. Поэтому вырастает ошибка. Угу.
Получается, что от количества столов, ну то есть от количества студентов, которые писали тест, у нас зависит то, какова вероятность обвинить кого-то в том, что они списывали.
Да.
И
Да,
заметить,
конечно.
что ответы похожие. Все понятно. Да, теперь я поняла. Все.
Okay. Okay. So after short discussion, we come to conclusion that we see that if we increase number of tables, we increase number of students who write the test. We understand that the probability to just of obtaining similar works that are similar not because students are cheating, but just because these two students are unlucky and they just by chance created similar works. This probability increase when we increase number of tables, and this is what we want to control, this probability. And actually, we can find the exact answer to this question. Let me do it. Actually, this is done with the following trick. What is probability to not accuse students at first table? So we believe now that nobody cheat. So null hypothesis holds. What is the probability to not accuse students at the first table?
99%.
Yeah, this is 0.99. And what about second table? Actually, it is the same. And now, what is the probability to not accuse neither?
But why the probability is not to accuse students at the first table is so high? Because they are first ones and...
because probability to accuse them is 1%.
Okay,
so probability to not accuse them is 99%. So this is 1 minus, sorry, like this. And actually first table and second table are equivalent. So probability for the second table is the same. And then what is the probability to not accuse neither students at the first table nor at the second table? So both events should happen. This event that we do not accuse students at the first table, the probability is 0.99. And this event that we do not accuse students at the second table. Yeah. Anna already get the general formula. And actually for two tables, this probability is just a product of two probabilities like this, because these things are independent. What happens at the first table is independent on what happens at the second table. And so our probability to falsely accuse them is also, these two events are independent. So this probability have to be multiplied to find the probability that both events happen. And due to independence. And so on. Actually, if we have 10 tables, we can write a formula So what is the probability that we do not accuse any student of 10 tables? So what is the probability of this event? So it means that we do not accuse students of the first table, of the second table, of the third table, of the fourth table, and so on. So what is the probability?
To multiply 0.99 by 10 times.
Yeah, something like this. And actually, this is well-known operation. I just have to find 10th degree power 10th of number 0.99. And what is the probability that we accuse at least one student, at least one table? So this is the probability that we do not accuse any table of these 10 tables. What is the probability that we accuse at least one table out of 10? So this is nobody accused. And this is the question about at least somebody accused. Why should I multiply by 0.01? Yeah, Anna is correct. In fact, these two events just they are complementary. If this event does not happen, then this event happens, and vice versa. You see? If it is not true that nobody accused, then it means that at least somebody accused. And if it is not true that at least somebody accused, then it means nobody accused. So these two events are complementary, and their probabilities have to sum up to 1. So we have here probability 1 minus 0.99 to the power 10. And this is correct answer. And let us use calculator to find the value of this probability. And my calculator says that it is about something like this. So it is about 10%, in fact.
Is it probability to accuse any of tables or any of students?
Our unit of consideration is table. So we either accuse some pair of students or not. We cannot accuse one student and do not accuse his or her neighbor.
Yes, I understand. Okay.
So this is why I write that we accuse one table. Okay, so we see that this number is actually close to what Natalia said about 10%, but slightly less. And this is the actual answer. And in fact, you can just try to increase number of tables. Actually, this will just increase this value here and this value here, and you can look how this number will change. Of course, if you increase this number, this thing will be also this thing will be decreased because this value is less than 1. And if you multiply something by a value that is less than 1, it decreases. And so if I increase this thing, I will also decrease this thing and increase this thing. So indeed, a probability to falsely accuse somebody will increase. What does it mean? Assume that I want this probability to be less than 1%. What should I do? Assume I want to make probability to falsely accuse anybody to be less than, to be not more than, not greater than. So again, I want to return to my initial significance level. But now I want to apply this significance level not to a particular table, but for the whole class. What should I do? How should I improve my procedure to make this happen? What should I do in this case?
You should somehow take into account the number of comparisons of situations
Mm-hmm.
in the formula.
In fact, we have this formula. And what can we change in this formula? This is number of tables, so this is number of comparisons, and we cannot change it. But I want this number to be less than 0.01. What can I do? What can I change?
In this case, just divide by 10.
Divided by 10 what?
The result, or like the...
No, of course, if I
the
want, if I just want to obtain this value somehow, I can just write it down and then I have this value. But I want the result of this formula that calculate me the answer to this question to be less than 1,000. Basically, what should I do as a teacher? If I see these calculations and I understand that I cannot, if I want to make sure that I will make a mistake with this probability, I want to control my probability of false accusation. I want this probability to be less than 1%. What should I do? How should I fix my procedure?
You should use less alpha in the initial procedure.
Exactly. I have to return to my to the beginning of my story when we consider it only a pair of tables, and decrease alpha here. So if I, for example, would use alpha not 0.01, but 10 times smaller here, then I will get another value here. I will get 0.999 instead 0.99. And in this case, I will obtain probability that I'm interested in. So one possibility is is to decrease initial alpha that is used to process one table. Yeah, consider alpha nu. For example, we can divide it by 10 by the number of comparisons. And in this case, let me find the same formula. So note that this value is actually 1 minus my initial alpha. So here I put 1 minus to the power 10. So it will be 1 minus 999 to the power 10. And again, let me use my calculator to get an answer. And this will be something like this. So we see that if I decrease this probability to make a mistake, at a particular table, of course, I will decrease probability to accuse some of the students. So basically, this is called Bonferroni correction. And it is the simplest realization of a way to deal with this problem of multiple comparison. And this is one way, rather universal, but not universally best, I would say. But it is really useful that you can apply this Bonferroni correction in any case, and you will obtain some meaningful result. So does it make sense to you from common sense perspective, at least? So basically the idea is the following. If I, for example, if I grade a small class, and if I grade, for example, the results of state exam in Russia that that involve all alumni of all schools in Russia, if I would use, so I should use different criterions when I accuse somebody in cheating, just because it is possible that some coincidence will be just due to chance.
Sorry, could you give the definition to this Bonferroni correction? Is this just the idea that we should decrease this alpha, or it is like that new alpha is alpha?
Divide alpha by number of comparisons.
Okay, thank you.
And if we have 10 tables, number of comparisons is 10, yes?
Under our procedure, yes, because I'm interested only in cheating between pairs of students. So in this problem, I just to simplify this problem, I just say that I have some independent tables, and I consider only communication between students who are at the same table. Of course, if I consider some more real life example, I have to take into account that, for example, students can communicate like this one, or they can use their phone and communicate like this one. And basically this makes analysis much more complicated. But I'm not. I don't want here to actually construct an exact estimates on how to estimate this kind of cheating. This is just an example, a real life example that shows you how this uh, problem of multiple comparisons manifests itself when you actually have several tests, several comparisons, and in each test, in each comparison, you can make a mistake.
Can you scroll up a little bit?
Yeah, sure. So, are there more questions about this example?
I'm interested, like, this Benferroni correction so it was created specifically for such situations with cheating, or
No, no. It is a very general. It is a very general statistical tool, and actually, we will discuss in a few minutes. We will discuss how to apply it to probably more situation that is more related to our statistical research.
Okay.
Okay, so let us continue. Now, let us consider completely different story, also about students, and also about test, but not about cheating. Different story. Actually, this is a real story. At some time, one of my colleague tried to test the following question: is it true that color of paper sheets that are used during the test affects the performance of the student at this test? So, for example, is it true that people write tests better if they use, for example, red papers or blue paper? And to answer this question, my colleague conducted an experiment. He conducted rather large exam. I think several hundred of students were involved. And he really obtained sheets of paper of different colors. Like some of them are red, some of them are yellow, some of them are blue, and some of them are white. So we have, for example, 4 colors. I think there were 4 colors in that experiment: red, yellow, blue, and white. So probably this sounds rather strange, this research question, but it is not very strange, because it is possible, for example, that red paper makes student more, I don't know, more aggressive, and it allows them to concentrate better and solve the problem. Or probably that's an opposite effect, that, for example, yellow color makes student more calm, and in this case they are more concentrated and they write their exams better. So I don't. It is possible that color affects these results of tests. And okay, how would you continue on this experiment? what would you do next? I have several hundreds of students, and I have a lot of red sheets of paper, yellow, blue, and white. What should we do next? So is it true that color of paper affects results of a test? This is my research question. And I want to conduct an experiment. How would you continue?
But what, maybe I skipped a little bit, but of paper, you mean the answer sheet, which they have?
It doesn't matter. This is sheets that you give them. For example, this is sheets that you use to write, and this is sheets that where their statements of problem are written. For example, it can look like the following. For example, here is like problem 1, and here is your solution. Here you write the solution, and the color of this paper is controlled by the examiner. So something like this. Yeah, before we can compare something with t-test, you have to collect some data. And how would you collect it?
Just to count the scores in each group separately. To count the scores in each group separately, and then
yes. But how would you distribute these sheets of paper between students?
Sonia proposed a really elaborated procedure.
Yeah, yes. Sonia writes that we can split the students into 4 groups, balancing the groups by some meaningful parameters, use the rankings of the students, for example, and give them the sheets of different colors. Yes, and actually we can make it even simpler. Yeah, in a sense, it is a good idea to balance the groups, but for our purpose, we can just distribute these sheets randomly. So every student have the same probability to obtain a sheet of any of these 4 colors. This will work enough for us because if we distribute these sheets randomly, we are sure that there is no any confounding effects. So if we see some difference, this difference will be attributed to these colors. Yeah. And after that, we have a table like this. So distribute randomly between students. And of course, we record which student obtained which sheet of paper. And then we have something like this. We have a data frame that consists of, for example, student. Here is color of paper. And here is a test result. For example, we have student A with the result 70, student B and we have result 80 here, and so on. Student C again with red, and result 65, and so on. student Z, yellow 60. So we have this table. What should we do next? What is your next step?
State the null hypothesis and alternative hypothesis.
Hmm?
State the two hypotheses. I mean the alternative hypothesis and null hypothesis.
Okay. What is your null hypothesis?
The null hypothesis is that the result doesn't depend on the color.
Exactly. Exactly. There is no difference. There is no difference between groups. Between groups. So between our four groups, between colors. So in other sense, we can say the following. We have formally we can think about this experiment in the following way. We have four populations. This is population of all possible results for red paper. This is population of all possible results for blue paper. This is population for yellow. And this is for white. And for each population, we have the corresponding population mean. So let me denote it mu red, mu blue, mu yellow, and mu white. And my null hypothesis, so all these values are population means. And our null hypothesis is stated that all of them are equal to each other. And an alternative is that at least two of them are different. No, sorry, this is alternative. So my model is the following. I believe that there are four populations, and my actual result in each group is obtained by random sampling from the corresponding population. And my null hypothesis is that all four population means are the same, so there is no dependence between the result and the color. And alternative is that there is some difference. For example, white differs from blue or white differs from yellow, something like this. So what is your next step?
Just compare the means between each other, but we expect that.
Yes, I can find sample mean for each group. For example, for blue, I have 75. For white, I will have, for example, 70. For yellow, I will have 81. And for Red, I have 72. Sample mean of test score, test results. So this is just sample mean per each group. Can I say something from this result?
We should compare, but now it seems that the difference is not big enough.
How can you decide what is big enough, what is large enough? So, for example, here is a difference between yellow and white, and average score of students who used yellow paper is 81, and average score of students who use white paper is 70. Isn't it a good evidence in favor of answer that yellow paper increase student score, and so every student who want to increase their score should use yellow paper? Can we conclude that we see some effect? Can we reject null hypothesis looking at these numbers?
No, we can't.
So what do you need to be able to make some conclusion? Or which tool can you try to use here?
We can use this Bonferroni correction and apply t-test.
Yeah. In fact, the first idea is, okay, we previously discussed that we have a t-test that allows us to consider these kind of comparisons. So to compare means in two groups, and to say, is it true that the difference between sample means that we observe is large enough to reject null hypothesis that the corresponding population means coincide with each other? And basically, the difference of this problem with t-test that we discussed previously is that in our previous problems, we had only two groups, like Moscow and St. Petersburg, as we discussed previously. And here we have 4 different groups. And what should we do now? For example, we can choose 2 groups, any 2 group, and apply t-test to these 2 groups. What can we try? Actually, as Natalia suggested 10 minutes ago, we can try to do pairwise t-test. So, for example, we can compare blue group with white group, blue group with yellow group, white with red, and so on. And assume that we see significant result at some of these t-tests. For example, we compare this yellow group and this white group, and we see that this difference is significant. Can we conclude just from this simple pairwise t-test that indeed we see that there is difference between yellow and white? Do we need something more?
But if we applied t-test, why not?
Yes, we applied. But what we want to do, we want to make sure that probability that we answer yes, so the probability to reject null hypothesis, provided that null hypothesis holds, is less than some significance level, like 5%. And if we apply t-test, we can be sure that, for example, in this particular t-test, probability to falsely reject null hypothesis is less than alpha. But we will report that we see some effect if any of these tests will give us significant result. So if any of these t-tests will say us that we have to reject the corresponding null hypothesis. Do you see some similarity with the previous story about cheating students? So at every of these pairwise comparison, we have some probability to falsely reject null hypothesis. And it is, for example, 5% here, or 5% here, 5% here, and so on. So probability to falsely reject null hypothesis in at least one test What can you say about this probability? At least approximately. I don't ask about the exact number here. In fact, it is impossible to find it because we don't have independence now. But at least if we compare this probability with this 0.05.
So we should multiply it by the number of comparisons.
So it is too large, but anyway, this probability will be larger than this 5%. Will be larger than 0.05. Do everybody understand why this is true? Basically, this is the same story as previously, but now we don't have students who can cheat or not cheat, but we have a t-test that can either falsely reject null hypothesis or do not falsely reject null hypothesis. And now again, we consider a case when null hypothesis holds, and we ask ourselves, if we apply this t-test several times, and in each time we have some probability to falsely reject null hypothesis, then probability to falsely reject null hypothesis in at least one case will be larger than 5% that we are interested in. It means that if we increase number of these pairwise comparisons or any other kind of application of some test to your data.
So I was right that in this case it's difficult to count, but we should multiply 0.05 by many times. Yes?
Actually, the exact formula that we used here does not apply. This formula will not be applied here because this formula relies on the independence of the results of different tables, which were an assumption in this problem. And it doesn't hold here because, for example, we have the same groups that take part in different comparisons. So we don't have independence here. But anyway, it will be larger than 0.05 because we have more opportunities, more ways to make this mistake, to make type 1 error. We can make this type 1 error during this test, or we can make this type 1 error during this test, or we can make this one type 1 error during this test. So of course, to make this error during one of these tests, this probability is larger than 0.05. So what should we do? How to fix it? In fact, we have two options, at least two options. Can you name me? The first option?
Use Bonferroni correction.
Yeah, use Bonferroni correction. That means that at each t-test, use alpha that is equal to 5% divided by number of comparisons. It will work, but it can be a little bit too conservative. So probably that we will be too strict with this option. And another option is to use a specialized test. That can work with several groups. And this test is called Anova. And I think that we can discuss it after a 10 minutes break. Okay. Any questions so far? Okay, so let us make a 10 minutes break and return at 1943.
But are we supposed to have a practical class after that?
Yes, I will still probably 20 minutes or 10 minutes. So we can continue. And let me explain very quickly how Anova works. So let me, actually Anova is exactly the tool that is used to solve this kind of problem that we discussed here. And it works by considering variances, as name suggests. And to explain how it works, let me draw two pictures. Let me consider two possible data sets. So I have score here, and I have 4 different colors on the horizontal axis, red, yellow, blue, and white. And assume that I have 2 pictures, and at one picture, my data looks like the following. So every point is an observation. So every point is a student and the result of this student. And the second picture is very similar to this one. So I will just copy it. And let me just make it a little bit more like this. So basically, I try to not change the sample average in each group. So I move some points to up and some points upper and some points lower, but preserving the mean value in each group. So it looks like the following. So these horizontal strokes are mean, corresponding group means. And so on both pictures, this group means and the difference between them are the same, more or less. At least I tried to draw them like this. And my question is, which picture is a better evidence against null hypothesis? So which picture?
The left one.
The left one is a better evidence against null hypothesis. Why?
Because the variance is lower.
Yeah, yes, we see that variances in each group here is smaller compared to variances here. And so basically we see that we can easily distinguish between these two groups, for example, or this group and this group. And here, this variance is rather large and basically, if we see this large variance, we understand that this sample mean is not too exact. If variance is small, then sample mean is a good approximation to actual population mean. Because if we understand that all objects in our sample are very close to each other, then it means that probably in population the same holds. So all elements there are also very close to each other. And it means that sample mean is a good estimate for population mean. And here, this estimate is not so good. And so this picture is less convincing argument against null hypothesis. So the left one. Because variances in each group are smaller. So the idea of analysis of variance is to compare these variances in each group and this difference between groups. Actually, we can do the following thing. We can consider a value that is called between group variance. And this is a value that is calculated like the following. We replace each element in each group by the corresponding group mean. And then we calculate, basically we calculate variance of these means. So we calculate how these means are, how far they are different from each other. And then we compare it with this in-group variance. So we can say something like this. We can find in-group variance. This is something like average of variances in each group. So I have this red group, I have variance here. I have this yellow group, I have variance here. I have this blue group variance here and this white group variance here. And then I will calculate some kind of average, actually weighted average of all these variances. And compare it with between group variance. Basically, between group variance can be calculated roughly as variance between group averages. Variance. I do not write an exact statement here, and just I don't want to get into much details with formulas here. But the idea is that it is something like variance between group means. So like we consider a sample with 4 elements. This element, this element, this element, and this element. And find variance of this sample. I simplify things a little bit, but it gives rather good intuition. And then we can say the following. If this between group variance is large compared to this in-group variance, then it is a good evidence against null hypothesis. So, for example, here, basically on these two pictures, between group variances are the same because the corresponding averages are the same. But in-group variances are different. And due to this fact, we can say that this picture is better evidence against null hypothesis than this picture. And then we can just get some numeric value that is calculated like you have to divide something by something. This is like between group variance. Divide by within group variance. And if f is large enough, reject null hypothesis. Again, you can ask, what does it mean that F is large enough? How large is large enough? And I will answer as usual that you have to believe that null hypothesis holds. So you have to believe that all these, that your data actually obtained from a case when all these population averages are equal to each other. And you can, under this condition, you can find the theoretical distribution of this value F. And then you can, actually this is known distribution. Actually, this is called F distribution, but we don't need to understand how this F distribution looks like. And then you have to compare the actually obtained value of F with this distribution and find the corresponding thresholds and p-values and so on. So this is how Anova works. And as you can see from the description, what is the difference between Anova and t-test? Basically, a short answer is that we cannot say that there is a difference because actually, if you have only two groups and you apply Anova to these two groups, you obtain a version of t-test, in fact. But Anova is more universal because it takes into account several groups and it works with these several groups not by pairwise comparisons, but by considering the whole picture. So it finds the whole differences between these values, these averages, and it works with the whole data. And so we don't have this multiple comparisons problem because we don't do multiple comparisons, we don't do multiple tests. We do just one test. We have one value that measures how far we are from the null hypothesis, and so this is a way how we can do this this kind of testing. So that's all that I wanted to tell you about analysis of variance. Actually, on the practical lesson, you can try applying Anova, and you can also try applying Bonferroni correction and see how the results are different. In fact, to return to this story about my colleague who tried to do this this comparison, he said that he tested yellow and white with t-test and obtained significant result, so rejected null hypothesis. But then I said that it is incorrect because you have multiple comparisons. And after that, I tried Anova, and it didn't give me any significant result. So during that experiment, we didn't see any effect of the color of the paper to the result of students. It doesn't mean that there is no such effect at all, because probably this effect exists, but too small to be detected by our experiment. But anyway, we didn't obtain some positive result at that time with appropriate statistical analysis.
But can we look at the formula one more time?
This formula?
Yes, between group group variance, but here it's like one number, but we have several.
This between group variance? Yes, it is one number. It is something like this. Assume that instead of considering this data set, you consider a data set that contains only 4 observations. One observation this, average of red group. One observation this, average of yellow group. One observation this, yellow average of blue group, and one observation this. And then you obtain variance of this sample with 4 elements. This is just one number. This number that shows how far these averages are from each other.
But they are, but the number should be different, no? Or at least it can be different.
Different between what and what?
Variance between red average and yellow average. And
you find average. Look, you find variance. Okay. Let me put it in this way. Consider the following new sample. This sample consists of 4 elements. This element, this element, this element, and this element. So this is just 4 numbers. And you can find variance of a sample that consists of these 4 numbers. This is just one value. You can find average of these averages, and you can find how far your values here are from this average. I simplify things a little bit because every time when I say average, you have to put actually some kind of weighted average. You have to take into account the number of elements in each group, but never mind. The idea is just to replace each group by its average mean, and then understand how far these averages between groups are from each other. So how far average of each group are from each other. Sorry, it's difficult to formulate.
But they can be far from each other. But the number, но разница между ними в расположении, она же разная может быть.
Может быть. Но суть в том, что чем больше разброс вот этих вот зелененьких точек, которые я нарисовал, так сказать, тем больше это аргумент в пользу того, что есть разница между группами. Есть разница между средними в этих группах.
Просто там написано, что between group variance это как одно число, но между красным, между средним красным и между средним желтым может быть не такая же разница, как между средним.
Я понял, что спрашиваете. Смотрите, значит, есть такая штука, значит, смотрите, у нас есть, мы определили, что такое дисперсия выборки. Значит, variance дисперсия. Значит, дисперсия выборки — это такая штука. Это там, сумма квадратов отклонений каждого числа от среднего всех этих чисел. Значит, вот для вот этой выборки мы можем посчитать эту самую дисперсию. Вот для этой выборки, состоящей из 4 зелененьких вот этих вот точек. Конечно, расстояние между этими точками может быть разное. Оно может быть, например, вот такое. Да? Вот такая штука вполне возможна. Но оно не должно быть одинаковым. Мы считаем как бы среднее отклонение от среднего. То есть вот у меня здесь, например, в этом случае будет... Что у меня будет? Ну вот где-то здесь у меня будет проходить среднее, да? И я посчитаю сумму квадратов вот таких вот разностей.
А я не вижу почему-то, что вы рисуете. Что
Зависла рисовалка.
Справа. Это все я увидела, что вы справа рисуете.
Вот. Значит, я рассматриваю сумму квадратов вот таких вот отклонений. Это одно число.
Да, но там же написано between group variance, то есть это разница между...
Это разница между группами. Это variance для как бы средних. Это variance выборки, которые составлены из средних. Проще всего про нее думать таким образом.
То есть среднее расстояние между каждой из этих средних. Ну вот смотрите, у нас есть sample means, и нас интересует разница между этими sample means, правильно?
Совершенно верно, да, совершенно верно.
И разница между sample mean с желтым и разница между sample mean синим не такая же, как разница между sample mean красным.
Это не страшно, потому что мы все равно считаем не разницу между ними попарно, а мы считаем среднюю разницу между числами и средним от всех 4 чисел.
Ага. Понятно. То есть мы считаем разницу между желтым и красным, sample mean, разницу
Да,
между
да.
желтым и синим, а потом и считаем их среднее.
Ну, я здесь зря взял тот же самый цвет. Давайте возьмем какой-нибудь другой цвет. Здесь вот такой вот, например. Вот пусть у меня вот это будет среднее от всех зеленых точек. И тут тоже. Может, так будет понятнее.
Мгм. Мгм. И то есть мы высчитываем среднюю разницу между каждой из этих sample means.
Мы высчитываем среднюю разницу, значит, средний квадрат разности между каждым из вот этих средних и средним, как бы общим, средним от средних. Вот этой вот штукой. This is grand mean.
Ага, ага, понятно. Да, понятно.
So I said, let me repeat what I said in English. I said that when we calculate this between group variance, it is a kind of variance between these 4 points. So variance of sample that consists of these 4 points. And to recall, we defined variance as a sum of squares of difference of actual values and average of all values. And so we find this average. I draw it here and denote it by grand mean. And then I say that my between group variance is sum of squares of these distances, these 4 distances. In fact, I'm cheating here a little bit in my explanation, because you have to take, in fact, you have to take into account size of all these groups, but let us skip it to begin with. Yeah, Anna, let me reiterate. In group variance. Within group variance, let me say that this is again average. Yeah, this is a different question. Let me say that we have 4 numbers, and again we can just find a kind of average, actually weighted average of these 4 numbers, and put it here. Actually, this is a good question.
Okay.
So this is basically how Anova works. More questions about Anova? Okay, then I think we can switch to the practical lessons. Ivan, please.
Okay, hi everyone. It's nice to see you again. And today we are going to do some Anova in R. And first, we'll do some data manipulation using tidyverse. We need to learn some new concept too. And actually, it's a good place to learn it, because it's actually pretty common task, and in this case it's a very meaningful task. So what we want to do, we want to aggregate data. So for example, let's have some data set. I will share my screen. Yep. Okay, and let's use this data set. We'll explore it a bit. Okay, we'll use this read CSV function from tidyverse. And first we need to load the tidyverse. Right. Okay. So let's read this data set and let's have a look what's in there. So we have many columns. And we want to test whether word duration is different among speakers. So we want to explore how many speakers we have. I think we have not so much speakers, right? So first of all, we can do it by table function that we used previously for chi-square test. Okay, so let's save it as a data frame. So, okay, we can just pull a vector with speaker. Then use it for table function. So in this case, we can explore how many, we can create a table of frequencies for a specific variable. I told you that I really don't like table function because it returns a class table that is actually inside mostly just named vector, and you don't have so many too many functions for work with it. So I will show you some more tidyverse way to work with it, and not only to calculate just number of occurrences per groups, but how to work actually on grouping variables in tidyverse. So in tidyverse, you have two main functions for that. First one is group by, and the second one is summarize, and you need to apply them both. Let's start with the first one, summarize. So remember that we used some functions like mutate and transmute to create a new variable. For example, I want to create a new variable that will be ID variable, right? I have a function row number that just returns the number of row. And if I do that, I create a new column where I have like something like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. So what was important about this mutate and transmute function? That when you apply them, you save, you preserve your structure of data frame, your structure of table. So when you apply it, you can return, you will get table returned that has the same number of rows, but you have like one more extra column or some more extra columns. Or if you use transmute, you just get just one column for the whole table, or two columns or whatever. But what is important, that you save the same number of rows, right? Okay. Send it to, I can just copy this link to chat and Zoom, and please resend it to Telegram too. So what was important when we use these functions to create a new column in a data frame, that actually we preserved the same number of rows, and that is a place where we have difference compared to this function that is called summarize, because basically in most cases summarize is used with functions that return just one value. Remember, with mutate, we could also do some creating a new column where we assign someone value. For example, we can create column mean word dur with a mean word duration. But in this case, If you return, if your function that you use inside mutate returns just one value, its value will be recycled for all rows. In contrast to mutate function, when you apply the same function inside the summarize function, you get just one row. You get just one column that you calculated, so more or less similar to transmute. But in this case, you get just one row with the result. Actually, it depends on the output of your functions that you applied. For example, if you apply a function range does very simple thing. It just returns minimum and maximum value for the for your vector. So if you apply range, actually you return not one but two values, so two rows. But it's just some modern tidyverse stuff. Basically, when you apply mutate, you get the same. You preserve your structure of data frame. You have the same number of rows that you had before. When you summarize, you just summarize your data frame in one row or like several rows, and that's it. So like squeeze your table, right? Actually, one funny thing about summarize that you can write it like this or like this with Z or S. It doesn't matter. It works the same. So both for British and American version. And creator of the main developer of tidyverse, Hedley Wickham, is from New Zealand, by the way. Okay, but what if you want to summarize by group? So what if you want to calculate mean word duration by every group? So you want to calculate mean word duration for BRS 02, BTE 03, and so on and so on. In this case, you need the second function called group by. Actually, if you apply group by, you can see that nothing really happens. Group by speaker. So what happened? Actually, not so much, but now you can see here group speaker 5. That means that actually the table is still the same, but you have some additional grouping attribute for now. And this attribute will change the way the summarize and other functions work if you apply these functions. So if you apply summarize now, I just copy this line of code here. So basically, I do the same as for here, but now I have a group by speaker in between, right? And let's have a look how it works now. So you can see that for every speaker, we calculated mean word duration. And of course, you can add some other variables here, or even just some calculations. So, for example, you can split by median or whatever, or I know we have so many articles, we have so many columns there. Aspiration. Okay, let's just use, for example, aspiration here, aspiration, and now we'll get grouping both for speaker and aspiration. And have a look, you have still some grouping variable here. So if you want to delete your groupings, you can use function ungroup. So you explicitly say that you don't want any groups. as attributes anymore. Okay. So yeah, now we can see, now we can have a look on average yeah, actually average word duration for every speaker. We can also calculate some other statistics. For example, standard deviation for word duration. Same, but SD, right? There are some other helpful functions that you can use inside summarize. For example, the one that is pretty simple is the function n. It just calculates the number of groups, the number of values per group. Right. So basically, it's something very similar to table. But also, instead of if you want to just calculate number of values per group using tidyverse, instead of using this group by speaker summarize n equal n, you can do it much more easily. Instead of combination of group by summarize plus n function, you can just use a function. And I really like this function because it's very easy. No, it's just not so. You can think that this function is not so important, but actually, one of the coolest guy in the tidyverse community, David Robinson, he conducts Tidy Tuesday screencasts every Sunday. And what he found that this function count is in the top 10 of his functions that he uses during this screencasts. So it's really useful function because you can combine some variables, you can sort right just inside the function these values, and so on. So in case you have in case when you have to calculate number of occurrences for every group, count is a really nice way to do that. Of course, you can do it in a more complicated way. You can add some, gloss. I don't know what is gloss here. But now you can have all combinations accounted, and you sorted them. Very nice, really, I really like it. Another important thing about group by, that you can combine it with other functions too. For example, you can combine it with mutate function. It's really really nice connection. Because remember that mutate function, it preserves the structure of table, and it means that it will be preserved, right? But what if you combine group by and mutate? Actually, I can show you how it will look like. Let's select something like the first few columns and last column. Great. So you can see that actually we calculated this mean value for every group and filled all rows with the same value for the whole group. it's really nice way to calculate something like a baseline. So you want to calculate a baseline for every group and then compare behavior of some variable compared to this baseline, And group by plus mutate is your choice for this operation. Another way to use group by to save humanity, for better data science, and for just your joy, for joy, is combination of group by and filter. And this is really my favorite. It's not the most famous one. Oh, I'm sorry, it's the previous one. But it's really cool one. So let's find some variable that is really that has variable groups in size. I don't know how to. Let's just try some. Just try count consonant, for example. Consonant. Yeah, somewhat. Yeah, I want to have something with more variable IPA. I don't know what is IPA. I mean, I know, but it's weird, you know. Oh, I think we have more options there. And let's say like sort it all through. Sorted it, and then we have a look. Okay. I mean, previous one was more interesting, I think. No. Okay, let's use constant. Let's use constant. Consonant. Yeah, we have different groups in size. One of them is very big, and some of them are pretty small. And what you maybe want to do, you want to take only bigger groups. So you want to filter only values that are part of some big groups, and you want to cut all values, all rows that has that belong to smaller group. And that's pretty much, it's really pretty easy. And here you need to combine group by consonant, for example, with filter. And here you use a function n and say n is more than 40. So here you want to calculate group sizes and select only rows that belong to groups that has size more than 40. In this case, you will return only bigger groups, right? Or you can do otherwise. You want to take only groups, only smaller groups that are, let's say, less than 20, for example, right? And you will get only the smaller groups. We can even check that it works. First, we need to ungroup, and then we need to count constant. You can see we have only small groups now, right? It's very cool. It's really so nice way to operate with this function. So group by makes you diverse tools make your tidyverse tools much more powerful. It's really nice. So, okay, let's return to Anova things. So now you can calculate mean. Let's return to this comment, and here you can see that we have some groups that are more or less like this of the same size. So yeah, it's better when you have for Anova group size that are somewhat similar, and that is similar enough. So that's pretty much okay. Another assumption, important assumption for Anova, is that your standard deviations, your variances for the variables are more or less the same. It's pretty much okay here. And there is also an assumption for normality that is really not that much important. I mean, yeah, you assume that your values are, I mean, if they're skewed, they're not very high skewed, but usually in most cases, it's pretty much okay. So here we clearly can do Anova, and let's try to do that. For doing Anova, we have many functions, many packages, and let's try to do it with the most easiest way, with a built-in function of. Actually, for R, you have several built-in ways to do Anova. The most popular one is our function. So like analysis of variance, right? And here we need to provide a formula. The formula is pretty much similar to a formula that you provide for t-test, for example. You have a dependent variable, word, duration, you have tilde, and then you use a predictor. Predictor here is Peter. And it didn't find object word dur. It says error in eval predvars data and object word dur was not found. What is my problem? What is the cause of this error? Please reply to me. It was not intentional, but it's really easy to find out what's wrong here. If you're, I mean, try to find the cause of this error, please.
Maybe you didn't specify the data source.
Yes, exactly. Thank you. So, right. We can do it two ways. The first one is like this. So we can specify data frame where we take these columns, or we can just use it on vectors. In this case, we don't need to. Yeah, we don't need to use specific data set. So both ways will work. Personally, I prefer this one. The second one, it seems to be a bit more clear. It's a bit easier to read, but it doesn't really matter. So, okay, and what do we have here? We have some sum of squares, okay, but where are our p-values? Where is our f statistics and so on? Don't worry. We need to save this result to some variable. Actually, we can do it without that, but let's do it in the most explicit way. Actually, we can do just actually, we can do it without it. Just using pipe. Again, the same thing we can do if you enjoy pipes as much as I do. You can do it like that. Provide to summary function. Summary function is a generic function, and generic function in R means that it behaves differently depending on what is the class of a object that you use as an input for this function. So if you do summary on a vector, it returns one thing. If you do summary on a data frame, it returns another things. If you do summary on of object, it's actually has some specific class. If you check it, actually even two classes, because actually analysis of variance is realized using linear modeling, and it's actually kind of linear model. Actually, just a specific case for linear regression. Anti-test is a specific case for linear regression too. Okay, so and here you can find this f value that actually just the ratio between mean squares for speaker. So mean squares for between subject between group differences divided by within group differences, and you will get this f value. Is this f value big? What do you think? Do you think that 140 is a big for f value?
This should be really big.
Yeah, it's really big because if your null hypothesis holds, your f value on average will be 1. So it will be ratio between mean squares for between compared to within will be just 1. And here you have a really huge ratio between and within, right? And it's very improbable result if our null hypothesis holds. We have very small p-value. Here's the p-value. And also it helps us with this asterisk. It's pretty nice, like it says. 3 asterisks means that p-value is less than 0.001, 0.001. So yeah, we can reject null hypothesis for this case, and we can say what? Like if we want to theoretically interpret the results, what can we say actually about our word durations for speakers?
That the word duration is different between speakers.
Yeah, but between which speakers? It's a tricky question actually, but try to answer that. Okay, just don't worry, because it's really a tricky question. Because for null hypothesis, is that we have that all mu's, all population means are the same for all 5 speakers, right? And alternative hypothesis says that at least one pair is not different. It doesn't say, so if you get p-values less than 0.05, it doesn't say which one pair. So in this case, we need to do some post hoc tests to find out actually which differences, which pair has have differences. And how can, I don't remember. I think you know. I'm not sure that you know about post hoc tests. I think you didn't cover it with Ilya, but anyway, it's very important thing to cover it again. So after you found out that, yeah, okay, something is different. Some pairs are different, but I don't know which one. The next step is actually to find out which one, or maybe not one, some of them. And do you know any other ways to compare difference between groups, except for analysis of variance?
T-test.
T-tests, right, exactly. We can compare each pair to each pair. We can just like select one pair and then compare, then select another pair and compare, and so on and so on. And this will be very boring, and we will not do that. And what we have instead, we have pairwise t-test. That will do this thing for us. But first we need to set some specific parameters for this function, and I will explain it a bit later. Okay. So we need to select like predictor, like grouping variable, and values. Also, we need to set this as noun for the first time. And like paired and pull as g, let's say false. Let's say false. Let's take it for now. And then we compare each one to each another. So we compare BTE03 to BRSO2, JJ04 to BRSO2, and this one is not significant actually. JJ04 to BTE03, this one is significant. SHG05 is significant. This everything. TT01 is significant to everything but JJ04. Right. But what is the problem here? When we conduct many t-tests, what's the problem that arises here when we do many t-tests? Actually, many people do not see the problem in that. It's actually just they do it like, okay, if you do just record more electrodes, just add some conditions, and anyway you'll find some significant results to publish a paper. And they do not think that they are cheating. They think that yeah, it's how it works. I mean, like, yeah, it's something like you mine these p-values like gold or Ethereum before they change to proof of stake. what is the problem? With this approach? And what is the potential problem here when we do compare 5 groups to each other? And we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 comparisons. Come on, I want to, yep, sorry?
We actually discussed this during the lecture.
Yes, I remember. That's why that's why I ask you. It's a similar to recall some things from a lecture. And what is the problem?
Yes, the problem is that when we perform multiple comparisons, the probability to get significant result is higher.
Yes, exactly. Exactly. You're correct. So,
can I also ask?
Sorry?
Can I also ask a question concerning your comment on this matrix? You said that there are probably 2 problems here, right? And the second one is that when we observe some differences between groups that are, I mean, we can't say really which groups differ from each other. It's hard
no, here we can say which group is different to each other. Like BTO3 is different to BRSO2. But for example, okay, we cannot reject null hypothesis, right? We cannot reject null hypothesis, but we cannot accept it for JJ04 to BRSO2. But at least we can reject hypothesis for BTE03 compared to BRSO2. But we have this problem of multiple comparisons, right? So how can we solve it?
Change the p-adjust method.
Yes, to what?
Bonferroni, probably.
Bonferroni, yeah. Yep. Ronnie, I'm not good in writing Italians. Okay, it worked. I'm sorry. I'm sorry. Actually, my scientific advisor was Italian, so it will save my soul for Italians, maybe. But okay, so it's complicated. Okay, so now we have corrected p-values. Actually, what is interesting that not so much changed here. So we didn't change our conclusions. Something that was significant is still significant. Something that wasn't significant didn't become significant, of course. But do you remember how Bonferroni correction works? What is the formula behind that? I'm not sure that we discussed it during the lecture, but I think we discussed it. What is the formula behind Bonferroni correction?
We discussed it for independent groups.
Yeah, just
the same.
Just multiply by number of hypotheses. So here you have 0.01, and for corrected you have 0.01, so 10 times more. That's simple. For here you have like 0.123, and even p that is actually not even p anymore, but adjusted p cannot be more than 1, so it's written as 1. And like here, for example, 0.063, here we have 0.63. So just 10 times more, because we have 10 hypotheses. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. As simple as that. You can do it even by your hands, right? You don't need to have specific function like Bonferroni, but you can. But you don't need to. You can calculate it easily by hands. Actually, even default p-adjust method is not Bonferroni in R. Check it, and you can see that p-value adjustment method is Holm. It's also called Holm-Bonferroni correction. Why Bonferroni is not default? Because Bonferroni is too restrictive. It's too conservative. And actually, you have some mathematical proof that Holm-Bonferroni still control level of alpha, level of family-wise error rate. So it controls that. So family-wise error rate means that you have false positive at least for one hypothesis for your family of testing that you do. So you want to control that you have this family-wise error rate, like you want approach. You want to control that that you have no more than, for example, 0.05 probability of getting at least one false positive result for all your family of hypotheses. And Bonferroni correction just move you to this space. So it solves the problem, but it solves this problem like antibiotics to your body. It kills not only bad guys, but also some real effects that you want to catch. So there is always a trade-off, because if you do your very conservative correction, you can you'll be on the safe side in terms of type 1 error, so probability of false positives, but you will be on not safe area for probability of for type 2 probability errors, for type 2 errors. Like if you actually have some effect, you'll get really more chances to miss this effect. Imagine you have like 1,000 hypotheses, and in this case you need to multiply by 1,000, and you have not so big samples. So it will be very hard to find some significant results, even if there is some effect. So there are also some alternatives to very conservative Bonferroni corrections, and the one that is used by default is Holm-Bonferroni correction. It's a bit more liberal, and it still solves the problem of controlling family-wise error rate. But there is also another approach to this problem of multiple comparisons that is called false discovery rate. It means that you want to control that proportion of your false positive results in the whole number of your results, your positive results. So you want to say that you want no more than 5% of false positives in the whole number of your positive results. So it's much more liberal approach. It's used, for example, in bioinformatics, so like genomics and so on. and sometimes in other fields, of course, too, because if you have really big number of comparisons, and you pretty much okay that you have some false positives, you can just collect them, and then you can test in further experiments these effects, but you're really interested to find some interesting results. So, but you want to control, of course, multiple comparisons somehow, but you want to do it in more liberal way. Another way, and to do that, you have actually several aliases. Here just methods is FDR. That is the most liberal approach, and it uses another philosophy. It's false discovery rate philosophy. So you control proportion of your false positive results in the whole bunch of results. Actually, there is only one way to do post hoc tests, post hoc analysis using pairwise t-tests. Another way is to use special post hoc tests that were designed for ANOVA. They actually, all these post hoc tests, they're independent to ANOVA. So they were called post hoc tests actually because many decades ago, you don't want to do another analysis just to check something, because every other computation is many hours, days, and weeks. And first you want to do some ANOVA to check whether you have at least anything. And then if you get some statistically significant differences, you are ready to explore where the differences are. Because one ANOVA is easier computationally than all comparisons for many groups. So now it's not really the case. We have R, we have smart and fast computers, but still it's called post hoc tests, like what we do after ANOVA. But that's pretty much okay. But we need to understand why it's so, because post hoc test, it doesn't mean that they're somehow related. Actually, QT-HSD, HSD stands for honestly significant differences. So it's like, honestly, like, I mean, really, trust me, I corrected for multiple comparisons for you. You don't need to think about anymore. So you can just get the results and relax. So QT-HSD does exactly like that. So it has some formula that ensures that this p-values are adjusted for multiple comparisons. And here you have the same, you have comparisons of each group to each other. And you have p-adjusted here. You can compare and find out that results are pretty much similar. So here you have what is not significant. Let's explore what is not significant. For all cases, that was the same. It was JJ04 to BRS02. And TT01 to JJ04. JJS to BRS02 and TT01 to JJ04. The same? Okay, some p-values are somewhat different, but we have the same conclusions for all corrections, and even without corrections, actually. So here we are pretty lucky because different methods leads to the same conclusions. In most cases, you have more or less similar picture, but not everywhere, because sometimes you have different, you apply different approaches, you get different results, and they're around 0.05. And what you need to do is to be honest about what you do. So that's why we try to use pre-registration in science, where like first we say what type of analysis we will do, and then we do this analysis without trying to just find the multiple comparisons technique that lead us to the results that we want to obtain. Okay. And here, what do you think, by the way, what do you have here? Lower and upper. Lower, and upper. Any ideas?
It looks like it.
Yep.
In Russian.
Yep.
But I'm not sure what they're doing here.
What? Yeah, I didn't hear. What do you say? What did you say?
I say quantili in Russian.
No, it's not quantiles.
Okay.
It's confidence intervals.
Oh yeah.
Lower bind for confidence interval and higher bind for confidence interval. And what's interesting, you can find it's confidence intervals for differences between two groups. And what is interesting, that where you have p-value less than 0.05, this confidence intervals, they do not catch 0. And in two cases where p-value is more than 0.05, these intervals, they catch 0. So you can see that this one is negative, this one is positive. So it means that 0 is somewhere between these numbers, right? The same here. We have -6 and plus 31. And 0 is somewhere between these values. And p-value is more than 0.05. So actually, when you applied confidence intervals and p-values, you'll get the same conclusions. So they say the same thing, but in different ways. With p-values, it's a bit more popular, but it's important that you understand confidence intervals too. In this case, confidence intervals it's 95% confidence intervals for differences between two groups. So I think that's all for today. Or maybe you have questions, I am ready to answer them. I think we covered a lot. We covered how to do analysis of variance in R. We covered how to conduct post-hoc tests. We covered different p-adjust methods and how to apply them. And also we covered a lot about tidyverse. An important thing about tidyverse, about this group by and summarize. And also group by plus mutate, group by plus filter. So now you have extended number of tools for tidyverse, and it's really nice tools for data manipulation. So I really recommend you to find some data and analyze them. Just play with it. Just explore them. Just find some data set about what you're interested in and play with it. Like explore, just apply groupings, calculate summary statistics, apply t-tests and Anova, try to visualize them, and so on. And it will be hard. It will be really harder than just doing some tasks, than just following lectures and following teacher on seminars. But it will, at some point, it will skyrocket your skills in data science to the moon. And it will be hard for the first few hours, days, and so on. But then you'll really enjoy it because it's really nice when you can do some fast analysis using these tidyverse tools. So I think that's all for today. Thank you for your attention. And see you again, I know, next week, right? I'm not sure. I think so. Okay, so bye, everyone.
I have a question, so I can ask.
Yep, of course.
It's probably a basic question, and I probably had to ask it during the lecture, but Anova is like, and this Bonferroni correction, although I know, is like for t-test, I mean like a grown t-test for comparison of means.
Yep.
But what if I have not means, but actual observations, like those that are, which we apply his square test?
Yeah, I mean, yeah, it depends on your hypothesis. So here, we didn't talk a lot about that here, but we have something like, actually, I don't know much about this data set, but let's say that we have some speaker and we calculate number like, or duration. I think it's duration in milliseconds maybe. So how long some, yeah, I think yes, what's in duration? So how long some speakers say some word. And what we're interested in, we want to compare whether some speakers are very interested here in specific speakers actually, whether some of them are longer in general than others in pronouncing these words, just words, any words. Yeah, and we are interested in differences in means, right? And that's why we compare means. It's a bit confusing that the method that we use to compare means is called analysis of variance. It's really confusing because analysis of variance is about comparing means, not about comparing variances. For example, if you want to compare variances, not means, you have Levene's test or other similar tests. So you actually have tests to compare variances to each other. So your hypothesis that this variance for this group is bigger than for this group. Actually, this test is even used to apply to test the assumptions for Anova, for example. Sometimes. I don't think it's reliable here, but people use it. Yeah, but what is your hypothesis can be different. For example, your hypothesis can be that I know this variables. So let's return to superheroes. Your hypothesis can be that, for example, at least for superheroes, males have more often blue eyes compared to females. And it means that you want to test for independence for two dependent variables. And in this case, you apply chi-square test, right? So if you are not sure what test to apply, start with your hypothesis. Start about formulating null hypothesis. And from this, it will be easier to understand what you need to do in terms of using hypothesis tests. And actually, we have, we didn't discuss it, but what if you apply ANOVA on two groups? Can you do that? It's a tricky question, but try to answer. We can discuss it. I will do it. I will select values and we'll discuss the results. Let's filter. What kind of, we have, for example, you want to take TT1, speaker to TT1, not equal, but in. So, I mean, try to think, try to give a hypothesis. Can you apply ANOVA on two groups or not?
Yes,
right?
of course.
Yes, yes, you can. But I mean, why not? Why yes?
Because it's like the same as t-test.
Yeah, actually, right. So ANOVA is a test for comparing means for more than two groups. And, or actually you can do it even for two groups. And if you apply it, you will have the same results as for t-test actually. So let's compare both words blur by speaker, right? And then summary. Actually, this functions were not created to use inside pipes, so it can be, it seems not so nice maybe. So another way to do it is to use something like package broom and either Eclipse or Tidy. Oh, Glance, sorry. But I really like this function. For tables. Nope. Wrong tidy. Okay. Can I use it like this? Sure. Yeah, yeah. But yeah, I have a big. I don't want to have it there. I will just get something. Just wanted to check what will be. Okay. And the same will apply not ANOVA but t-test. Actually, even syntax will be very similar. We will get actually the same p-value. I want to do without corrections t-test, so I will say var equal true to make like clear t-test, not Welch corrected t-test. So I will have the same p-value, and let's save it as t-test results to avoid some really crazy syntaxes. I mean, like You don't, okay. I will not scare you with combining pipes and operators, but I mean, it's fun, but I'm not sure that you're ready for this stuff. Even my employer said that do not show this stuff to people, to not frighten them. Okay, so we have that statistic. And what is fun, that if we get the second degree of this statistic, so to the second degree, we will get actually F value. So F statistic for the case of two groups is actually just square of T statistic. Ba-ba-bam. Is it cool?
Yeah, thank you. But
I mean, it's really cool.
Hmm?
It's really cool, I think, because, you know, I mean, this, you study this tests as separate tests, but actually that's really just one test in most cases. And this test is called general linear model, or even more generalized linear model. So it's important that you understand that these interconnections between different methods. So I think that's all for today. So it was nice to see you again. See you next week, I hope. I think I'm not sure about timetable sometimes. Okay, bye everyone.
Yeah, bye. Thank you.
Bye.